Warning: the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is the final video in a series on exponential and logarithmic functions. Again, you should have watched all the videos in this series if you're really trying to learn this stuff. You should know quite a bit already about this. This is set for pre-calculus students, so this assumes that you've already been pre-exposed to exponential functions and logarithmic functions, whether it's a natural log or base 10 log or base 5 logarithm, and you know how to deal with solving equations involving exponentials and logarithms, and finally, that you have seen the previous video on applications of exponential equations or exponential models. So in this video, I'm just going to talk about logarithmic applications rather than going through and doing a laundry list of them. We'll do a single example, but there's no reason to do a ton of them because they're all kind of the same example over and over again. So I'm going to read this out. This subsection is dedicated to logarithmic models. What you need to know about log models is that in general, you don't need to memorize them. If a problem is modeled using logarithms, you'll be given a formula. Likely your instructor will give you a formula for that model. And the reason for this is simple. The logarithmic scale is a way of taking vast rating systems and compressing them down into smaller scales. As such, they are more of a human construct than a natural phenomenon, which means that you cannot actually construct them yourself. They are, it's like somebody saying, oh, there's a rating system for professors. Okay. It's arbitrary how that rating system is built. It's not based on physics. It's not based on science or anything like that. It's just based on somebody's interpretation of how a model should be built. So, for example, D equals RT, that's a physics formula. You can rederive that. A squared plus B squared is equal to C squared for a right triangle. That is a theorem that would be true in any planet within our universe, within any society, and at any time. However, the decibel system, which is equal to log of I over I naught, it's just a rating system we came up with to state how loud a sound is. It's to give a rating for that sound. It's just a construct. That's all. So let's just do an example and then really talk about how they're all the same examples over and over again. The Richter scale is probably the most famous logarithmic scale. However, decibel scales, luminosity scales, any type of sensory scale is pretty much logarithmic for human beings. So they all follow this basic formula that the rating, which in this case we're going to call the magnitude, is equal to the logarithmic function of a ratio of things. A here is known as the amplitude of, let's just say, the earthquake, since we're actually dealing with Richter scales. But if it was decibels, it would be the amplitude, the power amplitude of the sound. And A naught would be the smallest possible measurable energy from whatever we're talking about, in this case, earthquakes. So the smallest measurable earthquake. Now, let's see. So the Richter scale uses that formula where A is the amplitude in centimeters measured at 100 kilometers from the epicenter. And A naught is the amplitude of the standard earthquake, whose amplitude is 1 micron, which is 1/10,000th of a centimeter. It should be noted that the centimeter measured with a seismograph is not the actual displacement of the tectonic plate. That seismograph is measuring almost what the shift of the tectonic plate is having, but it's not the exact same. It's not like a centimeter of movement on a seismograph means a centimeter of movement for the tectonic plate. It's just a measure of the energy released by the movement of the tectonic plate. So that being said, let's dive into this. Suppose we have an earthquake and it has amplitude 2.8. So seismic graph registers a movement of 2.8 centimeters. What is the magnitude of this earthquake? Well, that's actually not too terrible to figure out. Just zoom in here and I'll do A here. Remember, the magnitude is equal to the log of the amplitude over the base amplitude. And we have both of those in this situation. The amplitude is 2.8 centimeters. So I'll just write that down. And the base amplitude is 0.0001. Wait, I think there's one more zero there. No, that's right. 0.0001. And then you just grab a calculator. There's no need. Some people will expect you, you should compute out what 2.8 divided by 0.01. You don't have to do all that. You just grab a calculator. There's no need. So I'm just grabbing a calculator. Log of 2.8 divided by 0.123 and a 1. You can't see what I'm doing, but I'm doing this. And this is approximately, and I'll do what we would normally hear on the news. I'll round it to the nearest tenth. So this is a 4.4 magnitude quake. Now, when it comes to logarithmic applications, that's like the most basic question that you could be asked. It's evaluate, essentially. But most of them will have you compare. So what we're going to do is go to the USGS's latest earthquake data, and we're going to find a recent earthquake. And you could do this on your own, by the way. I'm going to showcase how you would find this information, and we'll just search for that, and we'll pick one of the most recent quakes and compare how many times more intense this earthquake was compared to the most recent earthquake. So here I am. I've just looked up USGS latest earthquakes, and then I'm going to go ahead and go to this USGS website. It gets here. I'm going to actually zoom in a little bit so that it's a little easier for everybody to see. And I'll go to the interactive map. And I'm based out of California, so I'm just going to look around in California for the most recent quakes. By the way, if you're based out of California, you know about earthquakes. Now, it's actually a pretty calm day in most of the world right now. So the largest quake that we had was, looks to be in northwest, basically Geysers, California. And I just zoomed in here to take a look at it. That's north of San Francisco, west of Sacramento, and it's in Northern California, but it's a 3.1. So I'm just going to write that down on my tablet next to me here. So we have a 3.1 out of the geysers. Now what we're going to do is go ahead and search for the USGS largest earthquakes. Here we are, just a quick, it was actually one of the first hits here. And I'm just going to scroll through this and find something that's more recent, because you can see this is 1960, 1964. We have one in 2004 off the west coast of Sumatra. That was a pretty devastating earthquake. But more recent, you had the Tohoku. I'm butchering this. Anyway, Tohoku earthquake, and that's in Japan. So we'll take that one. It was March 11th, 2011 in Japan, 9.1 earthquake. So there I have the magnitudes listed right there. We're doing part B right now. And the whole question really is, just take these two magnitude earthquakes and talk about how many times more intense was the earthquake in Japan versus the earthquake at the geysers in California. Because the logarithmic scale is a bit of a mental lie for us. We tend to think, 9 is roughly 3 times 3. So therefore, the quake in Japan must have been 3 times more powerful than the quake in California. But that is not how logarithms work. The logarithmic scale is very compressed. So if you write down the formulas for both of these, 3.1 is equal to log of whatever the power was for the earthquake at the geysers, divided by the smallest measurable quake, and we'll compare that to the earthquake in Japan. And by the way, I should probably label this A sub G, and we'll go over and label log of A sub T for Tohoku, Japan, over A sub 0. Again, the same measurement for A sub 0. These A sub 0s are the same numbers. I'm not even writing in those numbers. There's no need to, honestly. And so the question is, how many more times more powerful was the quake in Tohoku, I'm saying that hopefully correctly, versus the quake in the geysers, California? A sub t and A sub g are measures of energy output. They're not rating systems. They're actually how much energy was emitted during this earthquake. So let's go ahead, and by the way, that's usually in watts per square meter. So let's go ahead and solve both of these for their respective energy levels. That is, let's solve this first equation. Whoops, that's not an arrow. Let's solve this first equation for A sub g. If you raise both sides, use that circular argument, raise both sides, that's 10 to the 3.1 should equal the interior. Let me write that down. 10 to the 3.1 power should equal A sub g over A sub 0. And that g just got messed up because that's what my pen does. So the amplitude or the power level for the quake at the geysers, California today is 10 to the 3.1 power times A sub 0. And we know what A sub 0 is, but we don't need to put it in there. Just don't worry about that for now. So box that up. Now let's go over to the quake in Tohoku, Japan, and solve that again using the circular argument. 10 to the 9.1 is equal to the inside. So 10 to the 9.1 is equal to A sub t over A naught. Multiply both sides by A naught, and you get the following. 10 to the 9.1 power times A sub 0 is equal to A sub t. That is the power level, or was the power level, for the earthquake in Japan in 2011. Now, when somebody asks how many times more powerful is one thing than another, you can think of it this way. If you had $3,000 and I had $300, how many times more money do you have than I do? That sounds really weird for me to say that, but it's basically how many times more wealthy are you than me, I guess. And that is done by division. Your 3,000 divided by my 300, you have 10 times the amount of money that I have. And that is going to be the same idea here. You're going to take the amplitude of the earthquake in Japan and divide it by the amplitude of the earthquake today in the geysers, California. Well, the amplitude of the earthquake in Japan was 10 to the 9.1 times the base level. And the quake at the geysers today was 10 to the 3.1 power times, again, that base level. The base levels cancel, right? That's why I say there was really no reason to compute with those A naughts. They will disappear when you're asking this style of question. And using laws of exponents, this will be 10 to the 9.1 minus 3.1, or 10 to the 6th, or 1 with 6 zeros after it. That is 1,000,000 times more powerful. Now you can see why the logarithmic scale is very deceiving for our intellects. When somebody says, man, there was a 3.1 quake in the geysers today, and somebody else says, yeah, well, there was a 9.1 in Japan in 2011, it doesn't really give you how much more powerful that quake in Japan was versus the quake in the geysers. That quake in Japan was 1,000,000 times more powerful. That is super destructive. So you could do this, by the way. You go to the USGS website and look up quakes for all different time periods, whatever you want, and do your comparisons. This is how I build problems for exams, actually. So really cool way to deal with logarithmic problems. So rather than go through a laundry list of examples, it should suffice to say that most logarithmic applications follow the same pattern. You're given a formula, you're asked to evaluate it or solve it. Here are some of the typical formulas. pH level versus the hydrogen ion concentration of a substance, so that you can relate the hydrogen ion concentration and determine the pH, basically. Richter scale and seismograph displacement. Decibel level and the sound intensity, which is watts per square meter. And then, for example, magnitude of a star in terms of brightness. So all these, you should note, are based on perception. For example, decibel. we perceive by hearing. Magnitude of a star, we perceive by seeing. Magnitude of an earthquake, we perceive by feeling. pH levels, we perceive by taste. So all of these, this should reinforce what I've said earlier, which is the logarithmic function is really a human modeling function. It really models the world around us and how we perceive it. All right, that's all I really want to do in this video, because most of these applications are the same thing over and over again.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.